Welcome back in today's session, and we are going to start our discussion by reviewing some of the concepts related to our previous discussions on common mode feedback. We will try to address some of the good questions that were raised and that can help you in doing the simulation assignments as a part of this course. So, I will discuss the circuit implementation for the dual loop common mode feedback, where you are having two separate common mode loops for the first and the second stage of the op amp, and we will look into the we will try to contrast this method with the single loop compensation that we discussed, and we will try to understand the pros and cons of both the methods, and some of the details that we skipped earlier, transistor level implementation of the dual loop common mode feedback. We will go a little bit deeper into that and finalize the implementation, which will be useful for your simulation exercise. So, let us start with our op amp circuit that we had, the two stage fully differential op amp with the input Vi plus and Vi minus, and let us go for the common mode feedback for the two stages separately. So, we are going to employ error amplifier for the first stage and another second error amplifier for the second stage over here. Now, for the first stage, we can build the error amplifier that we discussed in our earlier sessions with split input pair, extracting the common mode voltage over here, and the output having an overall current mirror load, which gives us a sufficiently high gain from the error amplifier. You are having the V Ref CM1, which is basically the common mode reference level for the first stage coming over here, and if I call this VO1 plus and VO1 minus, I can put it over here, VO1 plus and VO1 minus coming over here, and the output of the error amplifier goes to our PMOS load of the first stage. And this is what we have done in the beginning while we looked into the common mode feedback of a single stage differential amplifier in isolation. So, we have already analyzed this particular configuration where you have the single stage diff amp compensated by an error amplifier, and we looked into the compensation scheme, and we suggested including coupling capacitors between the gate of the PMOS transistors and the output of the first stage, which is effectively going to give us overall mirror multiplication at this point. And therefore, if we remember, in the common mode half circuit, we are going to have this CC coming between the input and the output of the common source stage provided by this differential pair. And likewise, we can also look for the common mode feedback for the output stage. Before we do that, we have to look for the what is the output expected from the error amplifier, which is compensating the second stage, or which is going to provide the common mode feedback for the second stage. It is supposed to drive the gate of NMOS transistors, and therefore, if we use a similar structure over here to drive the gate of the NMOS transistor, it will require a VG close to, say, VT of this NMOS. So, if you talk about 180 nanometer technology, the VGS required may be close to 0.4 or 0.5 volt if your VDD is 1.8 volt and VT is around 0.4 volt. So, I am assuming that the VGS will be close to 0.4, 0.5 volt, and under that condition the output potential expected over here will be close to 0.4 volt, and that can push the input device into triode region, because if you look at the DC operating point, if you look at the DC operating point of this error amplifier, this is going to be behaving like a simple differential amplifier with current mirror load. If I look at the common mode response of this, suppose these two DC potentials as well as the VCM Ref are close together, the output DC point over here is going to be close, not the same, but at least close to this gate voltage of this PMOS load, which is basically VDD minus VGP, and again this VSG drop will be close to the VT of the PMOS, mod VT of the PMOS, which is again 0.4 volt, So, nominally this potential will be close to say VDD minus 0.4 or 0.5 volt. So, VDD 1.8 minus 0.4 or 0.5 volt. So, it is something like 1.3, 1.4 volt, and we are expecting that the DC potential that is required to drive this is of course much lower. It is close to 0.3 is going to be close to VT of the NMOS, so 0.4 to 0.5 volt. This is what we expect over here. So, if I look at the DC condition for this amplifier, nominally this potential will be in this range 1.8 minus 0.5, so around 1.3, it can go to 1.4 in this range. So, this is a minus sign and this is the range. Just let me distinguish this. So, this is also I am talking about the range 0.4 to 0.5 volt around, and accordingly we also need to see what is the VCM Ref that we are putting for the first stage in order to see whether this amplifier is going to work properly if I am using it only for the first stage. Now, if I look at the DC conditions for the current biasing, I am using some I bias with the help of this current mirror, and I also may be using the same I bias in these two branches. If I assume that you are having the same almost same I bias in these two branches which are being fed with the help of a current mirror with a reference branch, the two PMOS over here are also having I bias, whereas under DC condition what we expect is that these two PMOS transistors, they are going to have I bias by 2, I bias by 2, and these sources are identical. So, these current sources that we are putting, we are expecting that these are going to have identical dimensions, therefore, they are also going to sink I bias each, and as a result I am expecting I bias over here as well in both the PMOS load of the PMOS input device of the common source stage. And now, in this case I would like to ensure that the W by L of these two PMOS device, they are having certain ratio with the W by L of the PMOS device of the load. If I look at these devices, the tail current source devices, if I assume that their ratios are same, so for the same gate voltage applied by reference branch, they are going to sink the same current, and if these are supposed to sink the same current as well, I would like to make them double the size of these transistors, so that the gate potential that is applicable for these devices are also close to the gate potential coming over here. So, if you have a single ended op amp where the first stage is diode connected, there you directly have an insurance that the output DC potential over here will be dictated by the gate potential of the PMOS, and that also becomes the input DC point of the PMOS of the common source stage. But in this case, the output DC point is not defined. Gate potential over here is expected to be such that it supports the same IB by 2, IB by 2 flowing in these transistors. Therefore, the VSG or the gate potential over here provided by the error amplifier should be such that it is supporting the IB by 2 current in these two, whereas if I am expecting IB current in these two, the for the same gate potential I need to have W by L ratio over here, which is double. So, if this is W by L, this should be 2 times W by L, and also the gate potential of these PMOS should be close to the gate potential of this one, so that it supports the same IB, suppose the double the IB for twice W by L ratios. Therefore, this drain potential or the output DC potential under stable operation should be close to the required, it should be the output common mode that you get over here should be close to the VGP of this load transistor, and that VGP is once again going to be close to the VDD minus mod VTP value. Therefore, I would expect this VCM Ref to be close to VDD minus VSG of the MOSFET of the PMOS, which is once again going to be 1.8 minus 0.4, 0.5 volt. So, once again around 1.4. So, the VCM Ref value that I am getting over here is going to be around 1.4 volt, and therefore, under steady state when you have a common mode stable, the effective common mode input coming at these two inputs is also going to be around 1.4 volt. is that safe enough for this device, whether it is going to operate properly with such a large input common mode value, that also needs to be verified. So, if I look at this amplifier in isolation, the maximum common mode level that you can have for this amplifier, that is the maximum common DC level that you can have for the input device over here and here, that is going to be determined by the Vd plus mod Vt. So, the Vref CM max, if I want to find out what is the maximum allowed value of Vref CM that you can have, Vref CM 1 max, that is going to be given by the, I would call it Vd, let me call this Vd, Vd1 plus mod Vtp, because if assume that under DC condition you are having certain Vd1 over here, the maximum common mode level that you can have at the input is going to be equal to that Vd plus mod Vtp. So, if the DC bias under nominal DC bias, this node is going to have DC potential close to this one, which is say 1.3 volt, and therefore, the maximum input level that you can have, maximum input common mode that you can have over here is going to be the drain voltage plus the Vt of the NMOS. Sorry, this should be plus Vtn of the NMOS, because here we are talking about a particular drain voltage which has been set with the help of the direct connected MOSFET, and if you are assuming that these two voltages are close together under nominal operations, these two voltages are supposed to be close together, and as a result the drain voltage over here is set with the help of the direct connected MOSFET, that is VDD minus VSG, that is same over here. So, I am assuming that under nominal condition, under steady state operation, the Vd1 is having a value close to 1.3, 1.4, and under that condition the maximum input level, the maximum common mode level for this amplifier that you can have, or in other words the maximum reference common mode level that you can have for this is going to be the Vd1 plus Vtn, which is once again 1.3, 1.4 plus the Vt. So, it can go very close to VDD, the input allowed level or the maximum Vref CM level can go all the way to VDD. So, that is not a problem. So, having a higher required VCM is not a problem for the input device over here. So, even if it is 1.4, it is not going to bring this transistor into trouble, or the PMOS also into trouble, because from the maximum side this drain potential is being clamped with the help of the direct connected MOSFET, and for that particular drain potential I am just seeing what is the maximum allowed VCM ref that you can put. If you go on increasing the gate potential further and further, what is the maximum gate potential that you can have while keeping this transistor into saturation? That is going to be the drain potential plus Vt. Beyond that, the transistor over here will be entering into triode region. So, that is why we are first of all finding out the Vd1, which is going to be close to the DC potential over here, as long as these two potentials are close, and then for that Vd1, what is the maximum VCM ref that you can have, that is going to be equal to Vd1 plus Vt. So, that is going to be pretty large, it can go very close to VDD. So, 1.4 is not an issue as a VCM ref. So, this is one conclusion, and the second thing is the V out. So, as I said, V out is anyway close to the DC potential of the gate of this PMOS, which is also going to be the DC potential provided for the gate of these two PMOS over here. Therefore, it is going to be consistent. So, it is very much suitable for biasing the PMOS transistors over here. Now, one question can be how to obtain the VCM ref, because this VCM ref is supposed to be equal to the DC bias points over here, and what we are saying is that these DC points over here should also be close to the gate potential provided at this PMOS. So, for that I can create a reference gate potential of such a PMOS transistor and feed it over here. So, for that I can use a direct connected PMOS and apply the same reference VB, whatever VB is coming to this tail current source, I can apply the same reference voltage VB over here, and this is going to produce a VDD minus VSG potential over here, which is going to be close to the DC potential over here. So, in order to be if you are keeping these two devices same, then in order to get the same VG as this device, I also need to keep the size of this device twice these of the individual device, because these individual devices they are carrying IB by 2 IB by 2, and if I keeping this two same, then the diode connected MOSFET over here should be double the size of these individual devices, because this together will be carrying IB. Other option is you make this half, this size you can make it half of the tail current source over here. In that case, you can keep this device dimension same as this device dimension. Under that condition, whatever VG is produced over here will be suitable for biasing the VG over here, and this can provide the reference voltage. I can keep this as the reference CM over here for biasing my PMOS drain voltages. So, what it will do? It will enforce that the DC common mode level at the output of the first stage is close to the DC gate voltage expected to support IB, and if that is happening, I know that the same gate voltage is going to the PMOS over here, and therefore, looking at these ratios, it will also ensure that it is supporting IB current in these two MOSFETs.
Why are we keeping the VSG of all the MOSFETs equal to VT?
I am not keeping VSG equal to VT, it will come close to VT, because the current value that we are using in our example is pretty small, few tens of micro to 100 micro, and as a result the overdrive voltage will be small, VGS minus VT will be small, as a result the VGS will be close to VT. So, that is what I am assuming in all these examples. Any doubt in whatever I just did regarding the DC biasing, regarding choosing the VREF, and why this particular amplifier or air amplifier with NMOS as input and PMOS as load is suitable for biasing this PMOS gate?
Sir, can it affect in swing?
Which swing?
Means when we apply it in differential amplifier, if the bias point, output bias point is too high or too low, because the current
output bias point we have so far we have just fixed this bias point, and what we are ensuring is that the gate potential provided to this two PMOS is suitable for establishing the IB current in these two, and we are also trying to or expecting that these two tail current sources are also having IB current. We are just trying to match or just trying to establish appropriate bias point where the two PMOS are driven by a gate voltage. We will try to establish the current IB, and at the bottom side also we are having these two NMOS where we are expecting the same bias current IB. We have kept the dimensions over here same, and therefore right now we have not biased these two gates, that will be biased using a separate common mode feedback loop, but we are expecting that this voltage will be remaining close to B. As a result, this will also tend to pull or pull down the same bias current IB. So, the purpose of this is to get an appropriate DC point over here which allows the bias current IB in these two PMOS transistors, and at the bottom side we have these two NMOS transistors where the gate voltage is expected to be close to this bias point. Their dimensions are also close. As a result, we are trying to establish or trying to enforce IB in this NMOS also. So, we are just trying to ensure that both this PMOS as well as NMOS are biased with the help of this gate voltages to establish IB current, and then it will be more convenient to have the output voltage close to VDD by 2. Of course, that has to be taken care by the common mode feedback loop for the second stage, so that it can adjust this gate voltage a little bit across that VB, so that the output voltage is very close to the desired value. Swing here is more important, swing here is not so important. If you talk about swing, you know that if you are going for 10 to the power of 4 or larger gain, the gain of each of these stages is more than 100, this is more than 100. So, as we have discussed earlier also, the swing at this point is not so critical. As compared to this, the swing here is much larger, especially if you are talking about the first stage, few tens of microvolt of signal. Here you may get few millivolts of signal, and therefore it is not going to be so critical with respect to swing. So, even 100 millivolt of swing available over here is good enough, 50 millivolt is good enough, much more than required. So, I do not worry so much about swing here, but yes, swing will be more of a concern here, especially if you are having a second stage of front end amplifier with programmable gain.
Sir, why we need to made a feedback for biasing tail currents of NMOS?
because right now we have not fixed this one. So we have discussed earlier an example where there was a common feedback or common mode feedback loop for the two stages, where a single error amplifier was taking the output from the two differential outputs, and it was providing the feedback here. That was a single common mode feedback loop for the entire two stage. That's what we have discussed earlier. And here we are discussing two separate common mode feedback loop and looking at some of the details related to biasing. So just like we are concluding that this error amplifier with NMOS as input and PMOS as load is able to handle the required reference voltage, which is 1.4 volt, close to 1.4 volt, and it is also able to provide an output voltage which is suitable for biasing this PMOS. Likewise, we also need to argue that different flip topology with NMOS as input device, PMOS as input device and NMOS as load device will be required if we are constructing another common mode feedback loop for biasing these two. So far we have biased the output DC point over here, the common mode DC point over here with the help of first loop. We also need to do the same for the second loop. However, we see that the output DC point has to be close to the VG of this NMOS, and therefore it would be more prudent to look for NMOS load where the output DC point of an NMOS load differential amplifier will automatically be close to the VG of the NMOS, and let the input pair be PMOS. This is the reference one, and this has to go on the other side. I'll do that, and you have the PMOS current source. So here I can put my VCM Ref 2, which is the output common mode reference point. Now, what should be the output common mode reference point? This is anyway a DC bias, so I can, in the AC point of view, I can put it at AC ground. So this is again my differential amplifier, the same error amplifier topology. I have just flipped it. So the load device is now NMOS, input device is PMOS, the source current is also PMOS accordingly. And here I am going to get the VO 2 plus, and this is your VO 2 minus. I am going to get those over here, VO 2 plus and VO 2 minus, and I have to check the polarity. The way I have drawn is not proper, so I have to look at the polarity, that how it is able to satisfy a negative feedback across the loop and stabilize my common mode output DC level. So you can again trace the loop, assuming that because of some reason the output common mode level over here go up. If this goes up, I need to increase the gate voltage over here so that it is able to pull it down. So if because of any reason output voltage over here goes up, how will you bring it down? If I increase the gate voltage of these two devices little bit, it will try to pull it down, because the gate voltage of this PMOS is fixed, and because of some reason this voltage is going up, you want to bring it down. The only one of the option is that you increase this gate voltage so that the VGS term in the equation that becomes larger. As a result, it will be able to support the same current with a smaller drain to source drop. So it will try to bring the DC point over here lower. So in order to do that, if this is going up, I need this particular output to control the gate voltages. So the way I have drawn, I just need to flip this diode connection. I need to draw it this way. So this will be my output node, the high gain output node. So diode connection will be made on the other side, and then I can bring it over here and connect it with both the gates. So this basically this is going to complete the common mode feedback for the second stage, and we also need to see what is the reference common mode over here that is required. For the reference common mode, this is the output node, and we need to worry about swing, and for getting the best possible swing, I need to make sure that the output DC level over here, the common mode level over here, is biased midway between the two extremes, the V out max and V out min, and we know that V out max is going to be equal to VGP plus mod VTP, right. So V out max, V out I should call it VO2 max because I have defined it as VO2. So, just assume that the final V out I am assuming as VO2. So, V out max is going to be VGP plus mod VTP. Now, anyway the gate voltages of these 4 MOSFETs are similar, close. So, I can just write VGP plus mod VTP, and V out min is going to be this VB. The I should call this VB dash because this is the VB which is DC bias coming from some fixed reference, and this is the VB dash provided by the common mode feedback. So, this is going to be VB dash minus VT n. So, for a given VB dash which is coming from the common mode feedback amplifier, the minimum output level that you can have over here while keeping this NMOS in saturation will be equal to this VB dash minus VT n. And if I just put the numbers once again, if I look at the numbers, VGP as I said is going to be close to say 1.3, 1.4 plus mod VTP. So, this number is close to VDD, close to VDD, close to 1.8, and VB minus VTN also again it is close to 0, because for low current value the VB, which is basically the VGS of this MOSFET, will be close to VT, because VGS minus VT is small and you are trying to have lower bias current in this circuit. Therefore, this is also going to be close to 0. As a result, the output can have almost full swing from close to VDD to close to 0, and as a result I would like to bias my output DC point or the common mode equal to VDD by 2, this plus this by 2, so 0.9 volt, and therefore, this point I can keep it as 0.9 volt. And once again here we can see that why we have chosen this NMOS load, because the output DC potential, if I just look at this as a differential amplifier with current mirror load, if I look at the steady state condition in which the effective DC potential or effective potential at the gate of this PMOS and the reference PMOS is same, we are going to have same current in these branches approximately, and as a result the gate voltage being same, the drain voltage of these NMOS devices are also going to be same, which is going to be equal to VGS of NMOS. Therefore, the drain potential of these two NMOS is going to be close to VGS of NMOS, which is fed to these two NMOS also. So, that is for the output DC point is naturally close to the gate potential of an NMOS. Therefore, I would like to use the error amplifier with PMOS as input device, NMOS as load to bias the current sources over here. So, this biasing scheme will also ensure that the biasing current in the second stage is close to the biasing current that you are having in the first stage IB, because here what we have done is we have made the output DC point of this stage such that the VSG of this PMOS is suitable for supporting IB in these two branches, and likewise we have created a DC bias point at the gate through the help of this common mode feedback once again to support the same current. So, this will ensure that the current in these two stages are similar or close to the desired value. In case of a diode connected MOSFET, we already have output reference point. If you have a single ended op amp where you have a diode connected branch in the first stage, there automatically we have an output DC point over here equal to VG P of this MOSFET, and that basically sets the VG of the second stage. So, that ensures that you have a current over here which is going to be close to the current in the differential stage. But in this case, with the help of this overall common mode feedback in the first stage and the second stage, by choosing the references properly in the first stage and the second stage and the amplifier topologies properly in the first stage and second stage, we are able to ensure appropriate current bias. This is clear? So, a few more points regarding stability and its comparison with the single loop common mode feedback. We will be looking into that, and some alternatives that came up in our discussions earlier. We will be looking into those. So, any discussion required before we proceed, and we will be resuming our discussion after that.